Welcome to Python in Education, a series for teachers and students and anybody else. This video is on advanced 2D plots, which is part of this initial Python in Education series. It's this video down here. So if you're jumping into this video series directly to here, you might want to consider watching this video up here first, but it's up to you. And all of the videos here, if you want to watch those and jump directly to them, you can click on the box and just go directly to that video. So click on one of these boxes, or if not, stick around and we will do advanced 2D plots. Okay, so this video is a little bit different. It's going to be a little bit of a long video because it has all these different things that you see here in it. And you may not be interested in every single one of these things. You might be interested, for example, in only, how do I make a colored background, or how do I do multiple plots? So what I did is I set up this table of contents so that you can just simply click on any of these and jump to that part of the video, just to make it easier for you to get around. But if you want, just relax and we'll go through all of these in order. One of the things I'll do, if you decide to go through these in order, is I'll give more details in the beginning, and then instead of being redundant towards the end, I won't give as many details. So the ones at the end will go a little bit faster, and if they don't make too much sense, I might actually describe something in one of the earlier segments. Okay, let's do points and lines on a log linear scale. Often we do plots on what we call linear scale. So how do we add a log to that? So I chose as an example for this exponential decay because it comes up all the time, and we want to think about these kinds of things on a log linear scale. So here's a little script that does that. In the beginning, I have the usual comment that you should always have at the top to describe what it is, because you're going to want to save this and use it later. And what I point out here is that I'm actually going to show you three things. One is how to make fake data, which can be very useful, and so I'll cover that as well. Show how to plot points and functions on the same graph, and then of course the main issue here is how to use a log scale. So this describes just what this script does. We're going to pull in these libraries. I'm going to pull in two libraries into Python. One is NumPy, which I'm going to call NP, and that allows me to use a very beautiful array structure, which I'll talk about. And then the second one is the usual that we need, Matplotlib, to make the plots themselves, and I'm going to call that PLT when I reference it. So those are the two things that almost always are at the top of these types of scripts. Okay, so now what am I going to do first? First, I'm going to make fake data, and that's kind of a fun and useful thing to do. So let me just cover that really quickly. What I'm going to do is I'm going to set up a set of X points for my graph, and I'm going to use the NumPy linspace command so I can very easily generate points from 0 to 4, and I'm going to have 20 of them. And so those are going to be my fake data points, where I took the data, those 20 points. And then to make it look like real data, I'm going to add noise to it. And so what I do there is I use just another NumPy command, which generates random numbers, specifically from a normal distribution, like a Gaussian distribution. And that array, I want to have the same size as the length of where I took my fake data. So that's why I have size equals the length of this array up here. And then I multiply it by some constant that I chose just to make the plot look good. But of course, in reality, you would have, some real values of noise. Then, once I have my noise, I generate my data, which in this case is the e to the minus x. So I take my array of x values, and then I take e to the minus x of each one of those. So that creates a second array. And that's why I'm using NumPy arrays here. If I did this with a normal Python list, I'd have to loop over every single element and take the exponential of each one separately. But NumPy's smart enough to know what I'm trying to do. I'm trying to go from one array to another one, so it just does it automatically. And then I add to that the noise array that I made here, which has exactly the same length, and I add that into there, and I have my fake data. Okay, so that's how to make pretty simple fake data to sort of play around with. You can use that for lots of different things. Okay, then I have my theoretical curve, I call it, where I generate a very smooth curve, again using NumPy's linspace, which I cover in a lot of detail in a previous video, which goes from 0 to 5, and I want 200 points because I want that to be quite smooth. And then I use this NumPy exponential to generate a second array, which is the e to the minus x, where x are the values in this array. And then I plot it. Okay, so that's how I do the fake data and the real data part. And notice what I'm going to do here is I'm going to plot the fake data as points, and I'm going to plot the theoretical curve, I'm calling it here, as a very smooth curve. And so the way I do that is when I make the plot, I'm going to make the plot of the fake data be blue circles with nothing connecting them. Those are the points. And I'm going to plot the theory using a green solid line. And so I can get points and lines on the same graph. And if I just did that with the usual grid and legend and everything, I would get this graph. And you can see that this y-axis here is linear, and the x-axis is also linear. I have my fake data, which are these blue points, and I have my theory curve, which is the smooth green. And that's how I was able to generate that. Now, so how do I make the log scale, which is what this is all about? This is the command. After everything is done, I just tell it, make the y scale to be log, and I put that in quotes. And so what does that do? It looks like this. And so now I have a log linear scale where I can plot my theoretical curve and my data. And of course, this is really important in all parts of science and engineering and so forth, because for two reasons. Actually, one, you want to see what's going on down here where it's hard to see if you do that on a linear one, and also because you want to see whether some of these things that you're testing are actually exponential, and if you plot them on a log linear scale, they will be a line. And so this shows us that indeed we get a line when we plot an exponential on a log linear. And so it's a very useful thing to be able to do. Okay, so that is how you do a log linear scale. Okay, let's move on. Okay, next, error bars. Very, very important. Real data, when we measure real data, it always comes with some error. So we really need to keep that in mind and include that in our plots. Okay, so what I'm going to do here is the usual, a comment at the top to say what it is, and I'm going to import the libraries that I need. And in this case, I'm going to use lists and NumPy arrays at the same time, which is kind of a different example. So the first thing I do is I type in my data into these lists, which are just numbers in these square brackets. So this is a list of x values, a list of y values. It could be anything, voltage versus time, distance versus time, whatever it is in your data for whatever your experiment is. And then when you made those measurements of say it's voltage versus time, maybe you run the experiments many times and you get different values for the voltage. So you have some error associated with each one of those measurements. Well, you simply store those in a list as well. So pretty simple. And then to plot those, there is a command that you simply type, grab it in, pull it in from Matplotlib, and it's called error bar. And you simply give your data, y versus x, just like if you were plotting points, but you add to that y-e-r-r equals, and then you put the name of the list that contains the errors at each of these points. And that's it. Okay, so let's compare that with a theoretical curve as well. So down here I also I generate some x values, 50 of them. I find the exponential e to the minus 3x over 2, just as an example. And then I plot that as well using a smooth line just to show what that looks like. And so here is the graph that you get. So you can see the data are these blue circles with the dashed lines between them. That's using this format, does that. Notice that the error bars that I put on here, which are given by this list, are in green because I set the error color to be green. And you can also customize some of the shape of these error bars like I do with this. You can play around with changing this number to change the way the error bars look and get a nice graph like this. Now, when you make real measurements, it's also possible that you make errors in the measurements in this list. Like suppose that's a time. Maybe every time you run the experiment, you get a slightly different time, or your clock is slightly off, or you're measuring distance and your ruler is not perfect. It's possible also to have y and x error bars, but that's pretty simple. You just do x error equals, and then you have another list, and then you add another command like this where you replace the x into where you have a y here, and you can get the same thing. Let me show you what that looks like. You get this nice x errors and y errors, which is a far more realistic thing if you're making real measurements. And notice that when you do that, the legend up here reflects whether it's just point data with y error bars and or x error bars. And so the legend automatically updates itself for that. So that is how you add error bars to your data when you're making a graph. Okay, let's do bar graphs. Okay, bar graphs are really interesting and extremely useful. So why would you use a bar graph? Typically you use it when you're varying something with kind and not number. We often plot things versus time or distance or whatever. We're plotting a function versus some value, a number. Typically it's a number versus a number, but sometimes you want to plot things versus the kind of the thing. Like maybe the kind could be a color, red, blue, whatever. It could be state, New Mexico, New York, New Jersey, that sort of thing. And so bar graphs are really useful for doing that kind of thing. Okay, so how do we do that? Okay, the usual at the top, comment and bring in the libraries as usual. And then what I'm going to do here is I'm going to use normal lists. So these are just lists because I don't need to operate on them at all. So I don't need to use a NumPy array. So I just put these in a list. And as you saw in the previous example, I plotted both NumPy arrays and lists on the same plot, and there's no problem doing that. So either way is fine. Okay, so the example that I have here to make this bar graphs is I went out to the web and got some data on pennies. And I looked at the production of pennies at the Denver Mint, where they make pennies, and the Mint in Philadelphia, where they also make pennies, as a function of the year that they made them. And I said, okay, what a fun thing. Let's see how many pennies are minted every year at these two facilities and see which one makes more pennies. And so I just went out and grabbed this data. You can go out to the internet, grab some other data, replace these values with whatever data you're interested in, and play with it. It's actually a lot of fun. So okay, so that's the data, and I just got it off of the web up here at this website and just typed it in. Okay, now what am I going to do? When you make bar graphs, they're a little bit more difficult to make than some of the other graphs, so let me go through this a little bit slowly. So the first thing you're going to want to do, that I like to do, is set up the bar graph in a little section here. So I have a little comment here saying I'm going to set this up. The first thing I do is I set up the width of the bars, and you'll see in a minute why I do that. Now notice that the example I'm giving here is a little bit more complicated because I have two data sets. If you're doing one data set, some of the things I'm going to say don't matter and you can ignore them, but I wanted to do two data sets because that's such a common thing to do. Sometimes you might have 3 or 4 data sets you want to graph at the same time. So keep that in mind. So one of the reasons for controlling the bar width is to make sure that the bars for the different data sets don't overlap each other, and you'll see that in a second. Then what I do is I generate a set of x values, and notice I'm using NumPy's arange command, and it has a length of the length of these lists. Okay, so what that does, if you remember, is it goes from 0 to 1 to 2. It makes a list of integers up to the length, let me call that L minus 1, so that the total number in there is the length. Now, why do I need x when I have this list up here to plot against? The reason is that when you do a bar graph, this is what it's actually going to use for the x-axis. It's actually going to be plotting things at 0, 1, 2, 3, but what I'm going to do is use these as the labels. So even though they're numbers, they actually could be anything. They could be strings. They could be the names of, like I said, colors or states or countries or anything else you want. So that's why we need to set up a separate set of x values in a list. And here I'm using NumPy. Okay, and then I have a variable here for the opacity just because I wanted to be able to adjust the color. Okay, now once you've got that set up, it's actually pretty easy to make the bar graph because there's a command called bar. And so you simply call it in from Matplotlib with PLT, and it's called bar. And you do 2 of those, and you simply do Denver, which is this list, versus X. Notice it's versus X and not years, because years is merely my labels. And then I do what I'm calling Philly versus X, but notice I shifted over just slightly. This little shift right here keeps the bars for the Philadelphia data from not overlapping with the Denver data, and it shifts it over exactly the right amount by the width of the bar. And so that's how you get it to do that. So let's take a look at that. Here's what that plot looks like. So you can see I have nice titles, X labels and Y labels. I have a nice legend over here. And here's my bar graph. And you can see I have the years on the bottom, and I have the bars right next to each other. The green ones are Denver, and the orange ones are Philadelphia. Now you can see that I have this white space in here. You may or may not want that white space. Maybe you want more of it. The reason I put this white space is I like to have them a little bit separated. The way I got that white space was because I controlled the bar width. If I had made this bar width 0.5, they would have exactly fit and filled up this white space. If I make it smaller, I would have got two really thin bars and I would get more white space. So that's how you can control that. Okay. One last thing that you have to understand for bar graphs is when you're doing, especially when you're doing multiple bar graphs like this, it needs to know where to put this label. And I wanted the label to be right in the middle of the two bars, because it might try to put it at the left of the two bars. So what I did is I used this command right down here, which is called xticks. And what xticks does is it puts this label at these points. And that is where this and this finally come together. Make these labels at these points. But I never use these as the points. And you'll see that in a second, because I'm going to change these from numbers to actual strings, and you'll see what I mean. And then notice that I put the labels at X plus bar width, not at X. And that what it did is it would have put the label at the left edge, but by adding plus bar width, it moves it over this amount and then puts the label there, which is exactly in the center. And so that's something you want to keep in mind. And if you had 3 bars or 4 bars or 1 bar, you might want to tweak that in a slightly different way. But with this script, you can modify it and just play with some of those numbers, and you'll see what I mean in terms of getting it to work. I also introduce another command that's very useful, which is right down here, called tight layout. Keep that in mind when you're doing graphs where you have a lot of things next to each other, like these labels. Like this label 1999 is short. If it had been really long, it might have overwritten part of this label. And so one of the things that Matplotlib has is this thing called tight layout, which helps spread things out and keep things from overlapping too much and make things look a little bit better. So if things are getting a little bit crammed, keep in mind there's this tight layout command you can use to sort of spread things out a little bit. Okay, now let me prove to you that this works with actual strings and not numbers. And let me also show you at the same time how to make a stacked bar graph, which is a variant of this, which is kind of neat. Okay, so we're going to do a stacked bar graph, and we're going to actually do labels as strings. So let's look at how I modified this. Notice that now, over here, this is a list of strings, not a list of numbers. And so that is why I need to give the positions here of where to put these strings. Okay, so that's the strings part. And when you're doing bar graphs, often you'll be putting different strings in here, like I said, colors or whatever it is. Okay, now how do you stack? So the way you stack is actually really easy. You don't have to modify very much. I made essentially 3 modifications. One is I'm now going to put the bars at the same point. I'm not going to shift the Philadelphia bar over. And the second thing I'm going to do is I'm going to tell the bar command where I want the bottom of the bar to be. And I tell it that I want the bottom to be what's in this list. And of course, this list is simply the other data. And therefore, the bottom of the Philadelphia data will be at the top of the bar for the Denver data. And that's it. And then I also took out the plus bar width here just to put these labels in a very specific point. Okay, so let's put all of that together. Okay, so here is the original graph with numbers on the x-axis and the bars are side by side. Okay, now I switched it, and now I'm using this new script where I have actual strings. I could put whatever strings I want. I could put my name, your name, my mom's name, whatever I want in there. It could be anything I want. So that shows you how to put strings down there. Okay, and then now let's put the bars on top of each other. Now this is a nice thing to be able to do because it represents the data in a very nice way. It tells me this was the total that both of them did, and then I can see which one of them did more. This year, this was the total. This much was Philadelphia. This much was Denver. So it represents the same data, but it's much easier now to see what the total was for that particular year. So stacked bar graphs are actually quite useful. And just one final comment on these bar graphs. Notice there's quite a bit of white space. You can control that with the bar width, as I mentioned. And also notice that the label is right here on the left side of the bar. Maybe you want to move it right under the bar. You can do that by moving this point. I probably put plus bar width over 2, and it would move it right halfway across and put it right under. So you can play with those. Just grab this script and you can start playing around with it, modifying it, see what these different numbers are. Okay, so that pretty much covers how to do bar graphs. So let's move on. Okay, colored background. Let's do colored backgrounds and grids. Okay, how do we do that? So here's an example that I use from calculus. And basically the script is the usual stuff at the top. And then I use NumPy to create some x values. I evaluate some functions to get some y, just to generate some function. And then I do it again with a coarse grid. And I'm thinking about this as a calculus example because what I've done here is I've created these sort of fine points. I go from 0 to 2 pi with 80 points. And then from a calculus perspective, I say, how well can I approximate this function or its values or its slopes or the area under the curve or whatever by a series of lines? And how many points do I need? So here I chose 5. So this is a very coarse function. It goes from 0 to 2 pi with only 5 points. And then I create a separate array with those coarse values. And then I can compare, as I change the number of points, when do I actually approach something that looks like the actual curve? And this is sort of the concept of limits in calculus. Okay, but that's the example that I set up. How do I change the color of the grid and the background? Very easy. I introduce a new command, which I'll talk about in a lot of detail later in this video, called subplot. And subplot allows you a bunch of power to do things that you don't get otherwise. So it's a very good thing to know what subplot is. Here I'm using it in a very simplistic sense, and like I said, I'll talk about it more later in the video. You give it this value 1, 1, 1. All that is saying is that I'm going to have a grid of plots, and I'm going to have 1 by 1, and this is the first one. So I have 1 in the vertical direction, 1 in the horizontal direction, and this is the first one. So in this example, this isn't doing anything, but it allows me to access this command, which sets the background color. And that's what I really wanted to do. And that capability exists within subplot, and that's why I went in there so that I could access that capability. Let me clean this up a bit. Okay, then because I have kind of a dark background with that slate gray, I also change the grid here. Usually I just do plt.grid and then I have open and close parentheses. I don't tell it anything. Now I want to tell it something. I want to tell it to make the grid white. And I want to make it white because I have a dark background. So let's see what that looks like. So here's the graph. And you can see the smooth graph. And then you can see what happens as I change the number of points in the coarse grid. And you can see as the number of points in the coarse grid becomes large, one curve approaches the other one. Okay, so that is how you do colored backgrounds and colored grids. So you can see I have this nice slate gray background, and then the grids here are white. Black would also work, but I just wanted to show you, how to change that in case they are too similar and you can't see the grid point. All right, So now let's move on to annotations by adding text and actually an arrow to the graph. How do you do that? That's a very useful thing to do. So I'm going to actually add text and arrows to the plot. So here's how to do that. So the usual thing we're going to do, I'm going to use the example that I just used, and it's going to set up a smooth function from 0 to 2 pi with 80 points. Set up a coarse function, 0 to 2 pi with 10 points. And I'm just going to plot this as a line. I'm going to plot this as a set of points. And then I'm going to also have a gray, slate gray background and make the grid white. So we just covered that. Now what we want to do is add text and arrows to this. And it's actually really easy. Here's how you do that. Here's the command down here for text. And here's the command for arrows. And while I'm at it, I threw in that little bonus here, how to make the labels on the X and Y axis a little bit bigger. Okay, so let's do those three things. Okay, to make the text, I simply tell it where I want it. These are the coordinates. I put the text that I want, and I say how big it is. And so let's look at and see what that looks like. So here at the point 1.5, 0.55, so I go to 1.5, 0.55, and that is where I'm going to draw the text. And here is the text. Okay. Now notice that it goes on to 3 different lines. That is controlled by these \n's. So keep in mind, these are the points in the coordinate system that you're looking at. And I just simply tell it the text and how big it is. So this is an 18-point text. Okay, so that's how you put text. It's very easy. Just tell it what it is, where you want it, and how big you want it to be. Okay, now notice that once we see this, these numbers here, they're starting to look a little bit small. So how do we increase the size of those? So there we use X ticks and Y ticks, and so watch what happens when I change that to 20. That's a little bit too big, but I made it big enough that you could actually see the change here. So these are quite large now. And then finally, we want to do the arrow. The arrow is a little bit different, so let me walk through that. The way you do it is, again, you give the coordinates for the initial point, which is x, y, and you might think that then you give it the final point, like x initial, y initial, x final, y final, but that's not how it works. You have to actually give the change relative to the initial one. Okay, so here's what that looks like. So there's an arrow, and it's at this coordinate 3.2, 0.58, and then I move over 0.54 and I go down 0.65. That's the minus sign right here. Okay, so that is how you put text and arrows on your graph. Very useful for labeling things when you don't want to use a legend for some reason, and also a little tidbit of how to make these a little bit bigger. A little bonus there. Okay. Next, multiple plots. Sometimes you want to make a plot that has different graphs, but you don't want them all on the same graph. You want them just next to each other, maybe because it's too cluttered. So how do you separate a bunch of curves into multiple graphs, still within one graph, that you can save and keep as a unit? Okay, so the usual up here, a comment and bring in the libraries. And the example I'm going to use here is one of damped oscillations from circuits, springs, mechanical vibrations, some maybe for a physics lab or an electronics lab. I'm going to use that as the example. So what I do is I define here 3 functions. So this is my time function that goes from 0 to 8 with 80 points. And then I define an underdamped function, which is just using this function here, and I notice I'm using numpy because I want to go from an array to an array without a loop. And then I have a critically damped and I have an overdamped function. So those are the 3 functions I want to plot, but I want them on separate plots. I don't want them to be on top of each other. So it's really easy to do that. And the way that works is I break up the rest of the script into 3 pieces. Plot 1, plot 2, and plot 3. And actually plot 3, and then I show it. And now you can see why we have this show at the bottom, because we don't want to do anything until all of this is done. So this is the way to organize it, and here is how that works. Within each region, everything should be familiar to you by now. There's a plot, there's the function I'm going to plot, some customization. I have a legend and a grid. Same thing here, a plot, legend, grid, a label. So everything here should be very familiar. Okay, so where it's different is in the very first line. This one, and this one. And these are little cues that you're going to give to Python or Matplotlib to tell it what your intentions are. So what this command does is it makes a subplot. You give it these three numbers. The first one is the number of plots you want in the vertical direction, which is 3 in this case. The number you want in the horizontal direction, which is 1 in this case. And which plot are we currently working on? So what it says is there's going to be 3 plots in the vertical direction. And we have 1 plot in the horizontal direction. And right now we're going to work on the first one. And so it starts at the upper left and moves from there. So this is the one we're working on. Okay. Similarly, when we get here, this says 3, 1. So the same layout. Now I want to work on the second one. And so now this part right here is going to start filling in this part. And then similarly, when you get down here to this section, because it says 3, 1, 3, it's going to start filling in this part. So it's a really nice way to break it up, and it makes a lot of sense to organize it this way so that you can see very clearly what you're doing, and you can cut and paste and so forth and make it really easy. Okay, and then at the very end, as I said, when you're done, put it all together and make the plot. And here's what that looks like. So we have our 3 plots, underdamped, critically damped, and overdamped, all next to each other. So if I export this, so if I pull this up in the graphical user interface that comes with Python, I can print the disk drive icon and save it to like a PNG file. This will be one file. And so if I want to mail this to somebody or put it in a report or put a caption under it, it's now one complete unit. Okay. 2 other things to notice, just real quick, is notice where I put the labels. So here you notice there's no labels at all. Here I have a Y label, and here I have an X label. Why did I do that? You can actually put X labels and Y labels and titles actually everywhere you want within each of these sub-regions. The reason I did it this way is to make it look kind of nice. Because the Y-axis is the same for all 3 plots, I put one label on the middle one to basically be used by all 3 of them. And so that's why there's a Y label for the middle one. And then because the x-axis is also the same for all of them, there's no reason to do it under each graph. I just put it under the bottom graph, and that's why I saved that one for the very end. Now you could put Y labels and X labels on every single one of these if you want. You could put titles on every single one of these if you want. What tends to happen is it becomes very cluttered. So you want to use little tricks like this to make it look a little bit better. And earlier in the video, I mentioned this command called tight layout. This is a great example of where you might want to use tight layout. If you start putting titles and X labels on every single one of these, it's going to become very crammed, and you're going to want to use tight layout. Or, like in this case, if you have things that are on the same axes, you don't need labels for every single one. Okay, so that is how you put plots together. Let's do histograms. Okay, histograms. So in this example, I used the temperatures in Santa Fe as an example. Put a nice comment at the top to remind you what you did and bring in those very useful libraries. This is a very simple example. I went out to Weather Underground. I grabbed some data from there. I looked at the December 2014 high and low temperatures in Santa Fe, New Mexico, and I simply typed them into a set of NumPy arrays. And so these are the high temperatures, and these are the low temperatures. Pretty simple. And I could plot these like I've done in other parts of this video series. I could plot these values. But now I want to make a histogram. How do I do that? It is extremely easy. I simply use the hist command, and it makes a histogram. It couldn't be simpler. So here I make a histogram of the Santa Fe low temperatures. Here I make a histogram of the Santa Fe high temperatures. Now the only key thing you need to know is the number of bins you want to use. So when you're making a histogram, you're binning the data, and that's the crucial thing. And I'm going to use 10 bins. And I'll show you what happens when you change this number. And the rest of this is the usual customization. There's really nothing new here, other than when you're making a histogram like this, you might want to move the legend to a specific place. And so this is an example where I actually pass something into the parentheses of legend. Usually I just have the parentheses with nothing there. So you might want to use that. Okay, so what does that look like? So here is the histogram. The lighter blue here are the low temperatures, and the green here are the high temperatures. And so one of the interesting things you can see is the number of days that you get with these temperatures, the number of days you get with these temperatures roughly in this range. And you can see that sometimes the high temperatures are actually lower than the low temperatures depending on whether you're at the beginning or the end of the month. And so that's the way to make a histogram, which bins the data and gives you a sense of the distribution of values that you have in your data set, here using temperatures. So one of the things you could do, as I said, is change the number of bins. That can make a big difference. And so here I changed from 10 and 10, I changed to 5 and 5, which makes things look smoother. But of course, when you do that, then you have a wider range here and it gives you a little bit less information. But you can do that as well. And you can even do one of them in 5 bins and the other one in 10 bins, because these two numbers are independent. So you can make them whatever you want. And so that is a great way to make a histogram and show data in that way. But before we leave histograms, I want to talk about another example, which is just looking at distributions of random numbers, because this is really important when you're doing statistics or learning about statistics or learning about random numbers. I want to give a quick example on that, which uses this NumPy command called randn. This generates normal random numbers, in other words, distributed according to like a Gaussian, using the random package, which is inside of NumPy, which we brought in right here. And I'm going to generate 10 values. And I'm going to take those values and put them into a list, or in this case, a NumPy array. And then I just use the hist command to make a histogram, just like we just did. And I set the number of bins to be 40. I change the colors and give it a label, and so forth. Okay, so what's kind of fun about this is if you're learning about random numbers or statistics, what happens if I have a normal random number distribution with only 10 values? So I go out and I make a measurement. I measure 10 values. One interesting question is, can I even tell with 10 values that it's a normal distribution? Like you hear teachers talk about grading on a bell curve. Well, how many students have to be in the class before it actually looks like a bell curve? Like, what if there were 10? This is what 10 samples looks like. Doesn't look like anything. This could be almost any random number distribution that you can think of. Maybe it's uniform. I just happen to get 2 at that value that particular time. You know, who knows? But let's go back and change this number over here from 10 to different values and see what happens. So here's 100 values. Yeah, this might be a bell curve, right? It might be a normal distribution. What if we have 1,000? Okay, now it's starting to get filled in, and it's actually starting to look like a bell curve. Now, what if we made 10,000 measurements? What would that look like? And that's really starting to look like a bell curve. So just another example of using a histogram in a different way, not to look at data, but to look at statistical quantities and different distributions of random numbers. I just wanted to throw that in. Okay. Now, just to reward you for making it to this part of the video, I have a homework problem for you. So if you've watched this video on advanced 2D plots and you watched the previous video on basic 2D plots, I now have a homework problem. Can you make this graph, which is the temperatures in Santa Fe from the beginning of the year, the first day, to the last day, 365, with the lows represented down here, the highs up here, with a nice title, labels, and what's really nice is the shading that's between the curves, which goes from red when it's really hot and blue when it's really cold. That is your homework problem. So good luck with that. Okay, what next? You just watched this video right here. So presumably you've already watched this one. This will seem basic now. And now you can go click on any of these to jump to those videos. One thing I'd recommend, if you just watch this video and you haven't watched any of the other ones and you understood most of what was in here, I would go watch this video, because this extends everything that's in these videos to reading data from a file, because everything in these videos either was a function that I calculated or it was data that I typed into a list or a NumPy array. But often when we're thinking about data, whether interested in weather or climate or some other statistical property of something, we often get that data from the web from a file. So that's a really important thing to do. I would go watch this video because it extends these other videos in that direction. Don't worry if you want to try any of these codes. All the codes and all the plots in this video and all these videos are on the New Planet School Google Drive. So go in the description right below and there's a link to the Google Drive. All the codes are there. You can download them, you can play with them, you can modify them, do whatever you want with them. They're there. Don't worry about trying to type things in by looking at the video. Okay. All right, so that brings us to the end of this video. So, you're still here. You've lasted quite far through this video. Maybe you stuck around because you want to see a solution to the homework problem? Okay, that's fine. Let's go and let's do the homework problem then. Let's see how much progress we can make. This homework problem is actually quite challenging because it has two new concepts in it. One of the concepts is that it reads from a file. So as I just mentioned, the best video to watch next would be the video on how to read data from a file. So what I did here is I went to Weather Underground and I grabbed a comma-separated value file of weather conditions for Santa Fe, New Mexico. That's what this is. I open the file, and then this part right here reads all of the information in from that file, throws out the parts I don't want because I only wanted the max and min temperature from that file. There's lots of interesting data in that file. Threw out most of it, kept that part of it. And as I said, in that other video, I talk about how to read data from files. So I won't talk about that too much here. You can go watch that video to do that. So that is the first thing that you need to know, is how to get the data and read it in. And that way you have this data. Now the second trick that I used is I used what's called a contour plot. And this section of the code right here draws these color contours. So what I do is I generate a contour plot over the range of x and y values that I want and generate z values. So these z values are created to give the colors over this range of x and y. That's what that does. And this numbars just sets the number of color gradients that I want. And then this is a command that comes with Matplotlib that plots the color versus my y values versus my z values. So this is the trick to get the color. And if I did this, it would put color over most of the graph, depending on this range that I chose, which isn't what I want. So the trick to make it work is once I have that contour plot, I want to erase the parts that I don't want to see. So down here, I use this command called fill between. And what I do there is after I've drawn the contour plot, which is right here, Python's going to execute these commands in order. So it put the contour plot up there, but luckily I haven't seen it yet. It put the contour plot up there in its mind, and then what I do is between 0 and the minimum temperature, I fill it in with white. So it makes all of this area in here white and leave the rest of it with the color contour. And then the second command is from max temp, which are the values I read in from the file, up to 100, which is the top of the graph, fill that in with white. And so all of this up here is white. And the only thing that remains of the contour is the part that I didn't mark over with white, and those are the values between these two curves. So while it looks like I filled in between the two curves, where it's blue where it's cold and it's red where it's hot, what you're actually seeing is just the normal data plotted with white covering out the parts I didn't want you to see. So that is how you do that particular homework problem. It's a very beautiful graph, a great way to look at this type of data. So okay, so with that, thanks for being here. I hope to see you in one of the other videos.